very happy to talk about a super important topic on thermal interface materials for efficient battery designs. As mentioned already, I'd like to give you a little tour, actually not on all kind of different materials we have, but take you on a cruise how we develop and validate those materials and how we also using digital tools and how we come then finally to our different products to make battery design efficient, or at least the thermal management design. So just to introduce to you, Henkel is a key supplier in the automotive industry. I'm part of the product development in adhesive technologies for the automotive group, and we supply our different type of materials to the entire industries, no matter if it's an OEM or a tier one in the market. And when it comes to automotive components, we split our efforts according to different market segments. And the topic of today is e-mobility, where we capture all requirements and applications about the battery, the e-motor, and the power conversion ecosystems around the battery in an e-car. Henkel is free in using all kinds of different chemistries. That's pretty important for us, so we are not stuck to a certain resin technology like a silicon or polyurethane. So we could always pick the ideal chemistry, which then relates to the requirements of the product and the applications. So we're here free to tackle all kinds of different chemistries and also using those different types for our thermal conductive materials. We have and tackle all the different applications in a car, but also in other applications. So we do bonding, sealing, surface treatment in a car, specific cleaning, protect the different electronic systems, do electrical connections, and as the topic of today, we do thermal management. We have all kinds of capabilities to do fully automated testing on the equipment, on the materials. We have automated testing labs also to test our materials. Of course, we also do all kinds of durability testing, thermal testing. We could stress test the materials. We could dispense test at serious level. You will see this later how we do that, and could also enable for our customers different equipment layout and also do battery testing. Yeah? We have the support from different data scientists and different engineering groups to do all kind of CAD operated design and CAE. We do thermal modeling and combine the requirements from the material side already with requirements from our customers. Out of this, we develop also digital material cards, which we then use to recalibrate our systems and to do all those kind of testing. So to the topic of today, next to all the different materials we supply into a battery, today I want to talk a little about thermal gap filler materials and thermal conductive adhesive used in different battery designs, also for all kind of different battery cell types. For those who are not familiar, what is a thermal interface material and how it's used? Actually, what we do is we get rid of the air between a heat source and a heatsink or cooling device with the help of what we call thermal interface material. So we position a material, either a liquid material or a pad-like material, in between those two components, and the job of our thermal interface material is to transfer heat from hot to cool. Yeah, and best case will be to do this in a extremely efficient way to carry the heat away, but also relieve the stress during thermal cycling between the different components. Most of the materials need to be electrically insulating and then be conformable to fix all the mechanical gaps. Yeah, for example, here between a battery module and the cooling plate. And then, of course, under all kinds of different operating conditions, they need to be stable and perform all the time. So the key target is for those interface materials to find the optimum balance for a lowest thermal resistance and fill the gaps. So the material needs to be as thin as possible and as thick as necessary. And Henkel's competence here is that we do the formulation. as mentioned, we are not doing the raw materials. We somehow optimize raw materials if we are not able to get them in a certain quality or in a certain grade. But our competence is that we're using different type of polymer structures like silicons, polyurethanes, or epoxy, and using what we call functional fillers. That's mainly filler technology with ceramic nature. And depending on the type of filler and how we bring those filler in a certain filling rate and how we also pack those fillers together into this resin matrix, we make the material thermal conductive. Classically, the more of those fillers you put into a silicon, for example, the higher the thermal conductivity will be. But it's a little more complex when you do the formulation because any kind of filler, any kind of surface type of the fillers and how you bundle and build them together has not only influence on the thermal characteristic, but also on the overall rheology, the dispensability characteristic, and a big driver from the filler is then also the final cost of the product. So when we develop those thermal interface materials, as mentioned, we are looking at the resin, what we call the matrix. So that's the base material. So we either could use polyurethanes, epoxies, silicone material, silan modified polymers, or even acrylic material. And depending on the key requirements, if it needs to be super elastic or chemically robust, we pick those kind of raw material, and then considering all the requirements and effects you can have from the resins, we use different types of fillers which are relevant for thermal conductivity, for the achievable bond line, so how thin you can press the material, but also the dispense rate. We bundle the resin with a filler technology, and then we are still free to define the final physical format. So we are not a liquid company. We also could do on the thermal side, create with all those kind of raw materials, pad-like material. Yeah? So those are mainly used inside of a module when the battery cell stack is positioned into this shoebox kind of module. We also could do one component material or two component material, depending a little on the Q schematic customers looking for. So we are extremely free to operate with different matrix and resin types, different fillers, and create a different physical format of the product. When we develop the material, we extremely early also look at the different influencing factors to the reliability and overall performance of the thermal materials. Yeah? So what are the requirements long-term and short-term? How is the application look like? And how do we need to design this? Yeah? So you have different factors influencing the overall performance and reliability, such as the filler types, what kind of contact area we could create, what kind of filler package we're using. And we need to look also on the mechanical concept and how this thermal interface material is built into the application. So it's super relevant for us to get early on engaged with our customers to understand what are the requirements, what are the influencing factors on the application to really make a good design on the material. When we do the materials validation, I mentioned it already in the beginning, we have all kind of testing equipment available in our design and product development hubs across the globe. So our key competence centers are in US, in Düsseldorf, in Germany, as well as in Shanghai in China. And here we do the thermal testing on the product according to certain standards. We do, of course, all the mechanical validations by ourselves. So checking, for example, hardness, lap shear strength, tensile lap shear strength, elongation to break, and all those kind of characteristics of the material. We do all kind of dielectric measurements. We also have an Henkel UL certified UL lab where we could all kind of lifetime testing, CTI testing for high voltage application. We do the rheology measurements, so viscosity, creep resistant, and slump technology. We check, of course, the cure kinetics on the material. And we also could do the process validation, doing all kind of different dispensing studies from really small scale at the lab to extremely large scale, meaning we could go from the development, mixing a material directly into a mass production equipment and stress test the material and see how the flow characteristic on this product will be. Then we also do shelf life and aging studies. So here, for example, we have an environmental chamber with a vibration table integrated. So here we could build, for example, in mini batteries or smaller modules to see how the material performs. And then, of course, we also open to do customer-specific testing, running different agent studies or shaker profiles. Yeah. When we develop, you have seen we have the different blocks on how to build a material together. We're looking at the influencing factors on the reliability and performance, but we also have in scope already what are the influencing factors when it comes to the production performance. So the overall process is a key relevant topic we really look into already at a very early stage in the product development. So is a customer looking for certain cleaning risk requirement? What kind of metering or dosing equipment they considering for the mass production? Are they looking more for room temperature curing, or do they have an oven? Might not be relevant for batteries. You're not using there an oven, but we also do other thermal materials, of course. So how is the packing? What's the feeding equipment? That's all the blocks we putting together when we develop the product. For this, we also have, when it comes to process engineering or production, we started already 20 years ago, enabling process-relevant solutions and technologies to our customers. So we have a partner, equipment partner network together, where we're working with all those companies globally together to make sure that whatever we develop early on is already dispensed and stress tested on those kind of equipment. So when customers come to us, they either work already with one of those partners we have, or we could enable different partners to run the different products in their production. When we do develop the materials, and that's a little the easy way to showcase a little where we are coming from, we actually develop the materials. Meanwhile, on the computer, that means we do the formulations on a PC. So bringing all the different fillers together, the different matrix or resin technology, and then we get as an output an indication on thermal conductivity, density of the product, and rheology indication. We could do in smaller scale already since many years thermal simulation, and then we bring actually our simulation data together with the test data, the validation of the product, and we also do all kind of rheology measurement comparing the behavior of the product, and we do the dispensing in our application engineering centers. So it's a little going in circles from mixing the material, bringing some digital data together, and then doing the real practical testing on the material. What is different, reacting to the dynamics of the e-mobility market and also being faster, and what is also super important for Henkel is being more sustainable, really saving raw materials, saving energy, and of course saving time, is that we're using a lot more digital modeling and simulation tools as we have done the last 50 years. So meanwhile, when it comes to batteries, we could do structural simulation. What's relevant for this topic as of today, thermal management, we could either one-dimensional or three-dimensional thermal simulations on battery level, and we could also do a simulation on the material application of the product. So we could see how the material with different dispensing patterns, as you can see here, behaves under compression forces. Yeah? So we see where are the maximum forces when you, for example, build in a module or you press cell stacks together. And this is what we simulate, what we model with the help of digital data cards from our different materials. But we also could really validate those testing, all those simulation information going into a practical systematic. Yeah, and with the comparison between the simulation and the practical validation, we also able to recalibrate our simulation if we are off. That's super important and helps us a lot, as say, to be more sustainable and faster to the market. I mentioned already we have the capability to do the dispensing. For this, we have established in the different regions what we called battery application or engineering centers. That means at battery level, we are able to dispense and apply all kind of different liquid materials into a battery. So it's either our own battery where we apply material and then we do fast charging testing, for example, or customers bring to us their battery design and we dispense, for example, a thermal gap filler, thermal conductive adhesive, or any other material which is relevant to assemble and build the battery together. So that's really in every region to support our customers. And you can see here we could run different types of chemistry, different types of materials with a series level dispensing equipment. Yeah. To even support further, we just opened our battery test center in Düsseldorf in our inspiration center. That means after doing all the application testing on the materials, we could build or even use customer batteries in our test center, and in an environmental chamber we could do the fast charging and discharging tests. We could also do leak testing from the inside or the outside of a battery, and then, as I mentioned, bundle all those kind of information together to see how did our simulation work or the customer simulation work in relation to the real world and the realistic situation. So that's something what we could do. And I think when you look at overall this big picture, having the full material understanding, having the battery application center and the test center, that's pretty unique when it comes to e-mobility and developing those different types of materials supporting our customers. Excuse me. So with all that, we create a lot of data. And data, I think, are nothing worse if you not have them at a certain point available for the different people that we learn from each other. So what we also have, we have a platform called Albert. It's an innovation platform where all those different data from the testing, from the formulation, from the application will go together and are available for our scientists. Sorry. So what we do is we have fully automated formulation on the materials. So we have a robotic system formulating. So if a PD colleague in Shanghai wants to do some formulation tests on the mechanical behavior of the product, he could type in the formulation. And in Düsseldorf, the line will formulate the material and do the fully automatic mechanical testing. We have a cloud platform, as I mentioned, which makes all those data available. We have data analytics behind there, and we're using artificial intelligence and iterative methods to further support the development of our products. Excuse me for a moment. Now to the different materials. I think I mentioned it in the beginning, thermal interface materials. The topic is about gap filler materials. There are different type of materials available. Same as thermal conductive adhesive, which we call Liquibond. So different grades, different formats. And when it comes to a more modular to pack battery design, traditionally customers using gap fillers, and here we have different materials available, driven either by a market requirement or by an OEM dedicated requirement. So we have different chemistries available, also different thermal conductivity levels. So initially, many customers started with a 3 watt per meter Kelvin solution, and now with the optimization of the mechanical concept, they drop their requirements and are operating more with a 2 watt per meter Kelvin materials. The curing schedule is mainly designed for a room temperature cure approach. And then we have also different materials with different what we call squeeze flow characteristic. So there also is a trend from an earlier development towards a new one where you see there's a significant drop in compression forces. So there's a certain sensitivity on the cells and the packs. So we see a trend here on the gap fillers to be easier to be squeezed and faster in compression. James mentioned it already in the beginning in his first presentation that the battery design changes, or the main trend is moving away from a modular design to a design which is called skip the module, or then finally cell to pack or cell to chassis. the overall reason for that is actually that you reduce complexity in the battery. You, of course, also reduce weight and height and cost, simply to increase the energy density, which is then relates to driving range. So that's the main approach here, which means the battery stacks without a module housing them more or less, making the stacks or the battery cells a part of the mechanical structure of a battery. So they are an integral part. And for that reason, there's a strong move away from the gap filler, which are not that mechanically robust. So they are not bonding at a high level. And that's where we see a trend that people asking for what we call the thermal conductive adhesive. So that's the module bonding or the cell to pack approach. And also here we have different type of material, either epoxy based or polyurethane based, with different thermal conductivity grades from 1.3 roughly to 3.6, also with different density, everything driven again to room temperature cure. And as you can see here, also with different lap shear or mechanical characteristic. So that's the portfolio we have of today. There's still a stronger trend making the adhesives even more flexible. That depends a little on the battery design, and the overall trend on thermal conductivity significantly dropped from 3 down to 1.5 watt per meter Kelvin. So this portfolio helps really to address the topic of cell to pack and making the battery stacks part of the entire mechanical concept. What is not new, I think a lot of adhesive material manufacturers working on that, but what we have is a debondable adhesive solution for EV batteries. I think you all have heard maybe there's an increased relevance on circularity for the batteries. Yeah, you have the right to repair, all those kind of things. So OEMs and tier ones need to think more about how to make sure that you not just have a recyclability of the battery, but also making the system repairability in the field. And when you look now on the trend that we bonding everything together for lifetime reliability, there needs to be a certain mechanism that you also dedicatedly in certain areas, in case of a failure, could do the debonding, to make the battery repairable. And we're addressing this with two different triggers. One is a thermal trigger, which is actually a coating at the dedicated areas, which will be then triggered thermally and creates an adhesive failure either on the structural or on the thermal adhesive between the two components. And then the second trigger we have is an electrical delamination, what we called. So that's a mechanism we could integrate either in a structural or thermal adhesive, and then it's activated by a small current and a small voltage. So those two mechanisms are proved in their concept and already in stress testing at OEMs, and will help to really addressing this sustainability topic in making a battery repairable. Of course, it depends a little on the battery configuration, what kind of thermal system you use, what cell types are integrated, and what is the objective. So here it's a little different than just having a gap filler being designed in a battery. For both mechanisms, we need to understand together with the customer how is his approach on this repair concept. So there needs to be a very early integration in the design discussions, from our side also to the customer. So to sum it up with the last slide, next to all those different concepts we are looking, the different battery trends, for us it's super important to have an efficient design in path actually for an efficient battery. That means we need to, or we like to understand very early the key requirements, and maybe if there are any hurdles or drawbacks or any restrictions on a chemistry, for example. So we try to clarify very early what are the key requirements. Then we're making use of our circulating product development with the digital tools, checking with the customers also selection criteria at their end. And then what's also super relevant is then having this process relevant solutions. So really understanding what are the requirements from the application, how does the process look like, which finally ends then in a dedicated thermal interface material and makes it a final solution. So that's really, really important for us to have this kind of discussion with our customers. And for that, yeah, I'm done with my presentation. Thanks for listening and happy to take your questions.